All right. Thanks for tuning in to this offline session of OHBM 2023. I'm Vincent Taschereau-Dumouchel. Today I'm going to be talking about is there a way to dissociate the conscious experience of emotion from its non-conscious correlates? When we do task-based fMRI, what we typically do is let's say we're interested in studying the subjective experience of emotion. What we do is we're going to present participants with a task that will evoke emotion of interest, let's say fear in that situation, and you will have your contrast situation. You will do this to run your contrasts and narrow down in the brain what kind of region you think are associated with that specific emotion. So in that specific case, we might get amygdala activity. But as you know, there's a classical problem with that approach that can be easily highlighted if we replace the brain with just a fridge. So let's say we're trying to study how the fridge generates cold, then we might turn the power on and off on that fridge. And if we look inside, we might see that, well, actually the refrigerator light is pretty well correlated with the power on and off. So it's a valid assumption to say that essentially it might be associated with cold. But of course, it's a problem. It's a classical problem of correlation does not equal causation. So if we want to specifically know what generates cold in the fridge, well, we need to act on the refrigerator light, and that way we would be able to see, well, that you see that specific light is not associated with temperature. That's of course not easy to do. We can do it with stimulation technique, but it's not very easy to have a very fine grain effect on the brain using TMS or other stimulation technique. So what we've been trying to do is we've been trying to use decoded neurofeedback to do exactly that. The neat thing about decoded neurofeedback is that we can offline determine a pattern of brain activity that is the target of our intervention. Let's say we're interested in studying fear. Well, we can train a brain decoder to predict fear offline. And then in a real-time fMRI session, what we'll do is we're going to decode brain activity in real time, associate that feedback, that outcome of the decoder with a feedback that will be provided to the participants. And in doing so, we will hope to achieve a form of reinforcement learning. So that way, participants can learn to activate more reliably the pattern of brain activity we're interested in. And that way, we can, in the end, see if we can modulate the specific outcome that we were interested in. So let me walk you through a few of these experiments that were ran previously. One thing that is absolutely important with that kind of design is that it can be done in double-blind settings. Essentially, we don't have to say the target of the intervention to the participant. We can just run our decoder, and they can be trained without them knowing what's going on in their brain. So that's a very strong design that can bring very strong scientific results if they yield positive results, essentially. So let me show you a few of these experiments that were previously done. That first one was done by Ai Koizumi at ATR in Japan. So Ai-san first conditioned participants to two different stimuli. Here you have target CS plus or control CS plus. Then during the decoded neurofeedback experiment, she trained participants to activate the representation of one of the two CS pluses, and she showed that actually she could achieve a form of unconscious exposure, if you will, in that the amygdala activity decreased specifically for the target CS plus after the intervention, something that was not shown for the control CS plus, and she showed essentially the same pattern for skin conductance reactivity, which is a common marker of that kind of learning as well. We did something similar following up on Ai-san's study, but essentially this time what we did is we recruited participants that were afraid of at least two animals that were in our data set. So let's say people were afraid of cockroaches and snakes. Then we trained participants to activate the representation of one of these two animals in their brain. And we showed that, again, we could see a decrease in amygdala reactivity following the intervention. So you see here that for the target condition, amygdala decrease while it remains stable for the control condition. Similarly, we did this with patient recently, and there's this new preprint by Cody that show essentially the same interaction, but this time it's with patients that were already afraid of these of two animals in our data set. So that's very nice. That's three studies that seem to indicate that amygdala activity can be changed unconsciously. But one puzzling thing is that in none of these studies we add an effect on conscious fear. So participants showed a change in their physiology without them noticing anything, without them being aware of a change on the subjective level, which is a bit of a problem because if we want to devise a treatment for these kind of phobias, we would like participants not to feel fear as a result of the intervention as well. So we ran these studies to try to see if we can pinpoint a little bit what kind of brain regions can predict physiological responses or subjective affective experience. And what we found is that essentially here you have the red regions that were better at predicting the subjective rating and the blue regions that were better at predicting the physiological responses. So essentially you see that some regions in the middle frontal gyrus as well as the occipital region were better at predicting the subjective fear rating, and regions like the amygdala, insula, and VMPFC were better at predicting physiological responses. They were not exclusively predicting those responses. You see that amygdala was also predicting a bit subjective responses. But all in all, it seems that these two kind of measurements were associated with very different part of the brain. That meshes well with higher order theory of consciousness that has been put forward, amongst other by Joe Ledoux and Aquan Lau. But essentially, we showed using neurofeedback that we could have a change on physiology without affecting subjective responses, subjective experience. But essentially, that's not like an uncommon observation in the literature. There's a lot of situation where people will, for instance, avoid a specific situation and no longer show subjective fear when asked. You also have situations, for instance, where medication can block physiological reactivity without changing subjective experience. So there's all of these kind of dissociation that have been observed in the literature. But then it brings us to the question, can we actually modulate the subjective experience? We tried targeting low-level brain region previously, and it seemed like it didn't work out so well. So can we do this differently? So in a new experiment with Mathieu Roy at McGill and Taryn Berman, what we tried to do is we tried to change the subjective experience of pain this time. Mathieu has this nice signature that he's been developing with, amongst other, Thor Weger back in the day. The pain signature was trained in what can be called the pain matrix, but essentially it was a mask that was from neurosynth that was associated with um, the regions that were the most associated with pain in the literature, essentially. So they trained a decoder to predict pain ratings from these voxel, and well, here you have the decoder essentially. But then they noticed that some part of the pain ratings was not necessarily explained by that old signature. So what they did is they regress out the intensity of painful stimulation from the pain rating and also the prediction of the neurological pain signature, and it tried to predict the residuals of that regression. In doing so, they trained a new decoder called the stimulus intensity independent pain signature, which can be called SIPS, which is essentially trained to predict the residuals that are not predicted by NPS or by pain intensity. Why is this interesting? Well, essentially, it seems that this signature can predict a fair share of the variance that is not explained by NPS, and it's more associated with psychological modulation of pain. such as placebo effect and attentional modulation of pain. So we thought, let's try to modulate that pain signature instead of NPS and see if we can have an effect on subjective experience. So we tweaked our decoded neurofeedback approach a little bit to do this because this is essentially a whole brain decoder. We had to decode 300,000 voxels in real time to do so. So here you have essentially the real-time procedure. We have a few different receivers on the computer that will process each new image as they are recorded. They are then transferred and pooled in that collector instance, which then will send just the last of the feedback value to the display computer that will feedback to the participants in the scanner. So this has been done mainly by implementing decoding on a GPU, which is quite effective. Here we show that essentially to process one image and transfer it in the MNI space, it takes us about like 0.5, 0.6 second, and then computing the actual decoding by detrending, standardizing, and decoding the data. Well, it seems like we can do that in 0.2 second, which is substantially faster than using our old CPU approach, which would have taken around, 3.5 seconds or so here in blue. So that's quite interesting. It seems like we can do decoding in real time quite fast in the MNI space. And then here, just for a sanity check, we showed that essentially we can decode pain rating in real time sort of efficiently. So you have the dashed line here, where is the onset of a pain stimulation that was given in the scanner in real time. So you see here that that the correlation between the expression of the decoder and the actual pain ratings was essentially at its maximum, like about 6 seconds after the onset of the pain stimulation. And as expected, we see here that actually NPS and SIPs are not correlated. So it seems that they're sort of explaining different part of the variance, which is how they were trained, as I said before, and it's sort of like what we expected. So essentially, we see here that we can have a fair correlation between the prediction of the decoder and the pain rating in real time. So that's all good. So now, can we train participants to actually modulate their pain related brain activity? So what we did is, in a double-blind placebo-controlled intervention, we trained participants to up or down regulate the SIPs, and they were provided feedback as a function of the success of their training. So we ran a first pain calibration session before and a second one after. Essentially, we find the intensity of stimulation that will give us pain ratings that are of 50 on our scale. And then we just delivered that exact same pain intensity during the session and see how pain varies as a result. So first thing, here you have the expression of SIPs as a function of day. In yellow, you have the upregulation group. In blue, you have the downregulation group. So you see that as a function of day, participants in the downregulation group tend to decrease the activity of SIPs, while NPS seems to have no change. So essentially, we seem to be able to downregulate SIPs independently from NPS. The effect in the upregulation group was not significant. It may be that it was trending, so maybe it's just that we were a bit underpowered to show that kind of effect here. So essentially here, what we showed is that participants in the downregulation group could indeed be trained to downregulate their SIPs expression as a function of learning. And that learning was independent of NPS. Then we showed that essentially downregulation of SIPs during training was associated with the pain rating that participants were providing after the training. So essentially, the better they were at downregulating their SIPs, the lower pain ratings they would report after the intervention. And that was only observed in the downregulation group and not in the upregulation group. So essentially, to summarize a little bit, we can predict the pain rating in real time in the MNI space using our approach. It seems that participants can be trained to downregulate their SIPs independently from the NPS. And the success of SIPs downregulation seems to be associated with pain perception following the intervention. So that's very exciting. Maybe there's a way to train participants to modulate their subjective experience of pain using that approach. But one problem is that essentially we see that it's a tiny effect. We need to train participants over the course of many days to have a small change in the expression of the pattern. So what we are going to look into now is to essentially to try to develop co-adaptive systems where we're going to be interacting with the brain of the participant using visual display or using electrical stimulation, essentially. And we're going to try to change brain activity using systems that will learn to interact with our participants and see if we can achieve a better change in induction accuracy. Like, all right. So here are the people I would like to thank, and thank you for your attention. Bye bye.